Dear students, in this video we'll discuss some efficient implementation of the fast Fourier transform algorithm. In the previous video, you have seen the recursive implementation of the fast Fourier transform algorithm. As you already know, the fast Fourier transform algorithm is an algorithm to compute the discrete Fourier transform of a given polynomial. So this video will present the iterative FFT algorithm and a parallel FFT circuit, that is the hardware implementation of the fast Fourier transform. So coming to the iterative FFT algorithm, this iterative FFT algorithm has been constructed from the recursive FFT which we already discussed. By removing some of the inefficiency in that algorithm, one of the inefficiency which we can see in the recursive algorithm, and the same thing can also be used in the recursive algorithm, is to avoid multiple times or multiple computation of the product omega into yk of 1, which we can do once in the loop and use that value of t, the temporary variable, to compute yk and yk plus n by 2, that is the two halves, which as you know in the recursive algorithm only half the values are computed, the other half can be easily obtained by this type of operation, and then we are going to recompute the required omega value. The operation in the loop above which is multiplying the total factor omega by yk and storing the product in t and further adding and subtracting it from yk is known as a butterfly operation and can be represented as below. You can notice here the yks are going to be used for multiplication and addition to get the required values, and the same is represented in a block form in the right part of the figure. Now, to implement the FFT in an iterative manner, it is nothing but the recursive FFT. What it does is it recursively computes single coefficient from the coefficient vector and combines them in the required manner. So we need to know the order in which the coefficients get combined. This is because whenever the coefficient vector length is 1, it returns only the coefficient value, and if you see that algorithm, basically it is combining those coefficient value to get a given value. So if you analyze that algorithm and build a recursive tree, the recursive tree will show you that the FFT algorithm will divide the coefficient vector into two vectors in each call with containing even numbered coefficients and odd numbered coefficients. So suppose we consider a coefficient vector of length 8, then as shown in the figure, it is going to have one call with A0, A2, A4 and A6, another call with A1, A3, A5 and A7, and the recursive call with the even numbered coefficients will be further divided, and so on, until we arrive at the leaf nodes of the recursive tree shown here, which is in the order A0, A4, A2, A6, A1, A5, A3 and A7. So if you just pass the coefficient vector in this order and do the combining operation which is shown in the recursive algorithm at the end as a loop, we could compute the discrete Fourier transform in iterative manner. So we should first we should have an algorithm to do this. This can be easily achieved by what we call as a bit reverse copy algorithm. What the bit reverse copy algorithm does is, it is going to copy the coefficient values which is shown in a coefficient vector to a location which is whose index values are reversed. That is, the bits representing the index are going to be reversed. For example, if there is a value stored in the first location, let us assume the 8 coefficients which we are shown in the reverse in the recursion tree previously. If the indices of these values, which is let us say A0 to A7, can be represented in binary bits as 000 to 111, Now let us assume there is some value of say 10 stored in A1, that is 001. Now if you reverse the bits, it becomes 100, nothing but the value for index is now 4. So if you say copy the value stored in location 1 to the location 4, you are going to have A4 stored in the, or the value in 1 stored in location A4. Similarly, if it is 100 is reversed, it becomes 001. So if you store the previous value which was stored in 4, it will come to location 1. So what happens? The 0th index value will have the same value, whereas the array in with location 1 will have a value which was actually A4, but now will be stored in location 1. So it will be, we can refer it as the first, or A of 1, it will be referring to A4. So this way we can achieve what is the required ordering of coefficients. Now once this required ordering of coefficients is done, the iterative FFT computes the discrete Fourier transform by combining all the coefficients two at a time, starting from the leaf nodes, and this is achieved by the algorithm which is given in this slide. Basically you can see here the topmost loop for s is equal to 1 to log n is going only log n times, which is nothing but the height of the recursion tree which we had just shown. Similarly, it goes on computing or combining values. First, because the leaf node, it is n by 2. That is achieved by what we call as m to the power of 2 to the m is equal to 2 to the power of s, that is 1. So it becomes it goes 0 to n minus 1 by m, means the m value will be 1 only, that is it is going to shift by 1 and go on combining those locations, that is a of 0 and a of 1 will be combined, a of 1 and a of 2 will be combined. It is nothing but combining the nodes in the leaf node level, or the leaf level of the recursion tree which we have built. And then in the next go to the loop, when s goes to 2, it is going to combine only the values which have been already combined and stored in the first of these locations, and it continues until all the coefficients get combined, and hence at the end of this iterative FFT we are going to get the discrete Fourier transform. And the time complexity of this algorithm is also theta of n log n, which is shown here. If you see the loops, we can construct a mathematical equation for that, basically because the loop from lines 6 to 13 goes n by 2s times 2 to the power of s times for each value of s, and the innermost loops from line number 8 to 13 executes m by 2 or 2 to the power of s minus 1 times. Okay. So basically if you multiply that, the time taken for the two innermost loops is nothing but summation of s n by 2 to the power of s n by 2 to the power of s into 2 to the power of s minus 1, and this runs log n times, because the outermost loop from line number 3 to 13, it is log n. So if you reduce this, it is nothing but summation s going from 1 to log n by 2, and this is a simple, as the n by 2 is a constant for this particular case, I can take n by 2 out. It is summation from s is equal to 1 to log n of 1. It can be reduced to theta of n log n. Now the same thing which we have discussed in the iterative algorithm can be implemented as a parallel FFT circuit. Basically what we do is, the coefficients are arranged by this particular circuitry in the required manner, and then the omega values get computed and stored in the butterfly operations, and they are input like this, and hence the output vector y will be the discrete Fourier transform of the input vector a, which is connected in this particular fashion. The hardware circuitry is for 8 coefficient vector. The bit reverse permutation in this operation is implemented by the leftmost part of the circuitry, and the circuit consists of log n stages where n is the number of coefficients, which is generally a power of 2, and each stage consists of n by 2 butterfly operation, and these are going to operate in parallel or compute in parallel. As a circuit has a depth of theta of log n, it performs the total butterfly operations, all the required butterfly operations in theta of n log n time, and that is the time complexity of this circuit. Though the parallel circuit also takes theta of n log n time, the iterative algorithm also takes theta of n log n time. It is much faster because of the hardware operations. So this is our discussion, or this completes our discussion on the fast Fourier transform and its implementations, the recursive implementation, the iterative implementation, and the parallel circuit implementation. The FFT has a lot of applications, as we already discussed. It can be used for polynomial multiplications, finding the convolution of signals in signal processing, finding the properties of an image in image processing, and so on. So with this, we'll conclude. Thank you.